In power electronics converters, because the input voltage and also the load would always encounter disturbances, which will lead to the change of the output of the converter. In order to maintain a stable output signal, so we usually need to introduce the negative feedback to enforce the closed loop control. So in this section, we are going to study the basic knowledge of negative feedback for power electronic converter, and also let's derive the transfer function together. So first, let me plot a block diagram of a power electronic converter. We use a black box to denote the power processor. So this power processor contains an output signal. Suppose this signal is the voltage signal, Vt. You can also have the other kind of output signals depending on your controlling target. It could be voltage, current, or even power. And on the input side, there are three parameters which might affect the output. First one is the controlling signal as dt. So this can affect the output signal, right? And second one is the load signal. Load change might also lead to a change of the output signal. Third one is the input voltage signal. The disturbance at the input side might lead to the change of the output. So therefore, the power processor can be represented by a function as Vt equals to function f, which includes three variables, Vg, Iload, and dt. So for this group of input signals, we can classify them into two categories. One is VGT and ILOT. We call this as the disturbances, right? Disturbances. And for this dt, we call this as the control input. So our target is we want to maintain a stable output signal, right? No matter how the disturbance changes, we can always establish a negative feedback loop to actively control D to resist the variations of Vg and Iload. So here is the objective. Objective is that we maintain a constant Vt to be equal to a DC value as capital V, regardless the disturbances. So how can we achieve this target? We can introduce the negative feedback. So we sense the output signal using a sensor. So this is the sensor block with a sensor gain. And we feed this sensed signal into a comparator. This comparator calculates the difference between the reference signal and the sensed output signal. So here is the V reference, which contains the information at what level we want to maintain the output voltage, right? Then we feed this error signal into a compensator. compensator block. The compensator block helps to improve the stability of the closed-loop system. It can be designed on purpose, right? Then the output of the compensated signal is fed to the pulse width modulation block. And the pulse width modulation block contains the driving signal, right? And also the control signal and feed to the control input. So this is a complete closed-loop negative feedback system. Okay, now let's use a power electronic example, right? We use the buck converter to represent the example of negative feedback. So we plot the schematic of buck topology here. So we have the input stage as power input, which is denoted as VG. And we have the switch network, which contains a MOSFET Q and power diode D. On the right-hand side, we have the low-pass filter network. C, L, R. Here is the I load. And here is the output voltage. For this example, the target is that we want to maintain a constant output voltage. We consider the output voltage as the output signal. So we can use a sensor to capture the information for the output voltage. So here is sensor. Suppose the transfer function for this sensor is HS. And since the signal is fed to the comparator block, minus positive. And here is the input of the reference. And the output for this calculator is the error signal between the reference signal and the sensed output signal. We denote as VE as error signal. And we go through the compensator. Compensator is marked as GCS. And the output stage goes to the pulse width modulator. And goes to the gate driver. And the gate driver output is fed to the gate of the MOSFET. That is a typical power converter example for the negative feedback system. Okay, now let's look at for the power processing stage. So basically this part is circled as the switching converter stage. For this switching converter stage, we have introduced the principles to establish is small signal model, right? So here we use the small signal canonic model. For the buck converter, so we first plot the open loop small signal model. So if you still remember, right, for canonical model, it's kind of uniform model. So we have the input small signal source on the left-hand side, VG cap, and we place controlling part into a current source here as JS D cap, together with a voltage source here, whose value is ES times controlling signal DS. Then we go through a AC transformer with the same coupling point, and the waveline indicates that this is a virtual AC transformer. Turns ratio for this transformer equals to 1 to MD, where MD is the voltage conversion ratio for this specific topology. For buck converter is D, right? MD equals to D. And on the right-hand side, we have the low pass filter with LE C and load resistance. And also to model the load side disturbances, we introduce a AC current source here to model the load side dynamics. So this is iLoad small signal, iLoad cap in S domain. And also we have we mark the output signal here as the voltage across the load resistor, which we use VS to denote. For such a canonical AC model, we can express the output signal by the function of input disturbance, load disturbance, and the control input. So we can write the expression, analytical expression. So Vs equals to 3 parts sum together. First part is controlling part, GVD S times D cap, which reflects the impact of D, controlling input. Second part is GVGS times line small signal input. This means the contribution of the line input, right? Third one is the iLoad part. Because the current is denoted to be flowing down, so we use a minor sign here. Z out times iLoad. All those 3 signals are in S domain. So based on this analytical expression for the output signal, so we can say that there are 3 transfer functions. VGD, right? So where GVD is defined as the control to output transfer function, as the ratio of output signal divided by controlling signal. If we consider the impact of D, we will assume that the other inputs are 0. So given the condition that line input small signal is 0, load input small signal is 0. And secondly, we have the GVG is denoted as the ratio between output signal and line input. If we analyze the impact of line input, we consider the other small signal input are 0. And thirdly, we consider the impact of the load variation. So we will have the transfer function of Z out as the output impedance. Output signal divided by load. Given the condition that controlling small signal is 0, line input small signal is 0. So those three separate transfer functions can help us to simplify this model. Okay. Now let's erase the blackboard. Okay. Okay, we have erased the blackboard, and previously we can see that we can express the output signal by the sum of three parts. One is the controlling part, one is the line input part, and one is the load part. So our idea is that can we use blocks diagram to represent this mathematical equation? The answer is yes. So basically, we can do this. So we can use a calculator sign to sum those three parts. There will be three inputs. One plus. Second one is also plus. Third one will be minus. The three operators correspond to GVD, GVG, and the Z out part, right? So then we make up this block diagram. So here will correspond to controlling input part, which we use a block of GVDS. And the input for this stage is controlling input. And the second one, we plot the line input part as GVG. The input for this stage is line voltage. And thirdly is the output load current stage, which we introduce minus sign, right? So we can model the output current impact by the Z out. Block, and its input will be I load. So here is the output as Vs. So basically, this block is equivalent to this analytical expression, right? And next, we can establish the negative feedback. So similar as what we plotted previously, we have a sensor block to sense the output signal. So here is sensor. And feed this sensed signal into the calculator, which calculates the error signal, right? So there are two inputs. One is sensed output signal. One is the reference signal. So the difference will be equal to the error signal. And here is the sensor output will be sensor's transfer function times the output signal. So the error signal is fed to the compensator block, which is marked as GCS. And the compensated signal output is denoted as VC. And this one is fed to the pulse width modulator. We have learned that the pulse width modulator has its transfer function equal to 1 over m, Vm. And this goes to the controlling input to fully establish the closed loop negative feedback control, right? So here is PWM. Here is compensator. Based on this block diagram, we can try to solve the analytical expression for output signal Vs. Solve for output signal Vs. So the Vs V can be equal to the contribution of 3 parts. First part is this loop, right? The total input is the reference to the output. This is a closed loop. Second part is VG to the output. Third part is iLoad to the output. So first part is Vref times. So basically this is a closed loop control, right? We can analyze them one by one, step by step. Here I just put the result. It's equals to GC times GVD divided by Vm divided by 1 plus H times the loop gain, right? Loop gain. Loop gain will be equals H times GC times 1 over Vm times GVD. So which is H times GC GVD divided by Vm. Second part will be the impact of Vg, right? So when analyzing Vg impact, we consider the other 2 inputs are 0. So this will be VGS times GVG divided by 1 plus H GC GVD over Vm minus the iLoad contribution times Z out divided by 1 plus H GC GVD over Vm. So when we look at this full expression, we can see that they have some common parts. Basically, the denominator are identical. So which correspond to 1 plus loop gain. Right? 1 plus, this is the loop, 1 plus loop gain. So when we look at those 3 terms, we can find that they have some common part, which mainly exists in the denominator part, right? So we introduce a symbol as loop gain. So right, loop gain equals to this part, meaning the product of different terms through this loop. So TS is equal to HS times GCS times GVD S times 1 over Vm. So this quantity, we call this as loop gain. And we denote as TS. So by introducing TS, we can much simplify this set of equations. So we can rewrite the normalized format. So V out equals to, when we look at the denominator, right, it is just 1 plus TS. 1 plus T. And when we look at the numerator, this part is exactly T divided by H. And we keep the VREF. So this is a simplified expression for the VREF part. Second part can also be simplified as line input. So here will be just equal to GVG as it is divided by 1 plus loop gain. And here will be minus I load times Z out divided by 1 plus loop gain. Okay, so now, so in this section, we have introduced how can we introduce the negative feedback to control the circuit. And we utilize the buck converter as a typical example to derive the format of transfer function with negative feedback. Next, we are going to compare the negative feedback and open loop control, so we can illustrate why we need to introduce the negative feedback.